Hello and good afternoon, everyone. My name is Jordan Larson, and I work at the Technology Transfer Office at Marshall Space Flight Center in Huntsville, Alabama. I just wanted to thank everyone for taking the time out of their busy days to participate in the presentation. Throughout the webinar, all participants will be muted, but you can submit questions and we will answer them at the end. The Technology Transfer Program at NASA is in charge of evaluating all technologies invented for the space program. Any novel inventions that have commercial potential here on Earth are available on our website, which can be viewed at technology.nasa.gov. We currently have 1,400 different patents in our portfolio in 15 different categories, ranging from health and medicine to water purification processes. We have 3 types of licenses available: commercial and exclusive and non-exclusive, evaluation, and startup licenses. And without further ado, I would like to introduce our speaker today, inventor Paul Gradle. Paul has had a long and very successful career at Marshall and will be presenting on one of his latest inventions, the Laser Wire Direct Closeout technology for rocket nozzles and advanced heat exchangers. And with that, take it away, Paul.
All right, thank you, Jordan. Can we go to the next slide, please? Okay, so I think Jordan gave you a background. I work at NASA Marshall Space Flight Center in a liquid rocket engine component technology branch. We're responsible for the entire life cycle of components, and you'll see later an example of some of those components specific to liquid rocket engines, specifically nozzles and chambers. We've been working on a lot of these technologies for the past 10 years or so we're excited to present this to you today. So if we can go to the next slide. So agenda for our discussion today, I'm going to provide some background and motivation for why we developed this technology. We'll go through an overview of the process itself. I have several examples of hardware that we've fabricated to increase the technology readiness level, or the TRL, of this technology, including some hot fire testing in a relevant environment. And then we'll wrap up at the end and take any questions. Next slide. So providing a background on why did we develop this specific technology. So over the last couple decades, we've been looking at a variety of techniques to advance channel wall nozzles for liquid rocket engines. So in liquid rocket engines, the combustion chamber and the nozzle itself are a complex heat exchanger. We use the propellants to actively cool the wall. We have to contain those propellants within the channels, regeneratively cooled or actively cooled channels, to maintain low enough wall temperatures to operate in the extreme environments. And one of the challenges has been, how do you close out those channels? And the pressure in those channels can range up to several thousand PSI, in some cases 6,000 to 10,000 PSI, very thin walls so that we can minimize weight on that. And there's been several traditional techniques that have been developed over the last 60 years or so using brazing or plating closeouts, but there's a lot of challenges with some of those traditional technologies. So we wanted to develop a technology and application of that technology, which you'll see throughout this presentation. So specifically, the technology that we'll talk about is the Laser Wire Direct Closeout, or LWDC. This is an additively manufactured base technology, and we've been developing a series of demonstrator pieces and hot fire test nozzles using both monolithic, bimetallic, and multi-metallic materials, which allows us to optimize a bunch of different configurations for liquid rocket engines. We started a lot of this research in about 2014 with the process development. The technology itself was conceptualized in about 2012, and to date we've increased the technology to a TRL of about 6 with hot fire testing in a relevant environment, which I will discuss. So again, our goal of this technology was to evaluate alternate manufacturing methods with the objective of trying to reduce the fabrication cycle and, of course, the costs that come with that, and improve the performance for large-scale channel wall nozzles. You can go to the next slide. So I think it helps if we can see an actual overview of what a channel wall nozzle looks like. Again, we've provided this for both bimetallic and monolithic applications. So with monolithic, you're using a single material in this. Traditionally, we're using a stainless-based material or an Inconel-based super alloy. We can use these for generally lower heat flux applications. For bimetallics, we are using a copper liner on the inside for the increased conductivity, and then we're trying to close that out with a superalloy or a stainless based material that has a higher strength to weight to minimize the weight on that. And there's two images below. For some reason, the image on the left is not showing up properly, but the image on the right, you can see the monolithic configuration. So we have the hot wall, which is where your hot gases would be in liquid rocket engines, and the series of channels in there with the channel lands or the ribs, and then the backside or the closeout of that. So traditionally, to make one of these, and I'll show some images of this, is you'd start with the liner, you would slot the channels, and then you would have to plate or braze a closeout on that. And of course, those processes can be challenging. Sometimes there can be high scrap rates on those, and you have to get very tight tolerances on trying to close that out properly. So one of our objectives was using the LWDC process to form that jacket in place, which I'll show later. And of course, the image on the left-hand side is supposed to be a bimetallic configuration. So your liner would instead be copper with a superalloy or a stainless base closeout. So let's go to the next slide. So again, just trying to dial in on why we developed some of this. We looked at a lot of different technologies that are out there. In the different fabrication processes for nozzles, which can also be applied to advanced heat exchangers in different industries as well. But if you look at the traditional fabrication process, we would start out with a liner being fabricated, a variety of methods to go about forming that liner. Then you have to introduce the channels into that liner with a very thin hot wall. So those channels can be formed with a variety of traditional methods as well. And the real challenge, and where we've spent a lot of efforts and a lot of development over industry for several decades, is how do you go close out those channels? And a variety of methods have been developed for that. And a lot of the standard methods, as I mentioned, include brazing and plating. There's been some laser welding methods that have been evaluated. But one of the things that we were going after was, again, trying to form that jacket in place so we could minimize the piece part count on that, develop a robust bond with this, and do it for a variety of materials, both monolithic and bimetallic. So you can see where the laser wire direct closeout fits into the overall fabrication process, and I'll get into this in a little bit more detail as well. Next slide, please. So the process, why did we need this? And I think one of the questions that comes up, and certainly in the world of rockets, additive manufacturing is a very hot topic, and it's something that we're making heavy use of. And of course, this technology is based on additive manufacturing. But I think when people hear additive manufacturing, they generally think of the laser powder bed fusion technology. And certainly we've made use of a lot of that technology, and industry makes use of a lot of that technology. But one of the reasons and one of the motivations for developing the laser wire direct closeout was for the scalability of it. If you look at laser powder bed fusion, or SLM, selective laser melting, you're limited in the build box. There's some new developments trying to increase that build box, but when we look at a lot of the nozzle applications out there, both domestically in the US and internationally, the nozzles get to be very large scale. So for instance, the RS-25 nozzle, which is where we're targeting some of this technology, is about 90 inches in diameter and about 10 feet tall. So obviously the laser powder bed fusion or selective laser melting technology is not going to get you there in terms of scale. So this is, again, another one of our motivations for pushing this technology forward. Next slide. Okay, so I'll provide a quick overview of the technique itself, and we'll get into some of the applications on it. So with Laser Wire Direct Closeout, as the name says, we are using a laser beam as our energy source. We are feeding a wire into the melt pool to create the closeout. And if you look at the image on the right, what we're doing with the technology is we've gone through a lot of development on how to actually make it feasible, how to make it work. And you can see some of the references down there. There's a couple patents on the technology, and there's several papers that we've published in regards to the technology. Is a lot of the challenges are in the angles at which you have to deposit. Some of the shielding gas that goes with, some of the tooling that goes with this, and then the approach itself, combining all of those. So again, looking at the picture on the right-hand side, what we're doing is we start in an area of stock. We're assuming that the parts that we're fabricating are axisymmetric, similar to a rocket nozzle on this. So we have the nozzle that has been fully slotted. So all of your channels are in there, and you have an area of stock that is designed into your part. So you clad a few layers in the area of stock at the bottom of the liner there. And then as you progress up further into this, 80% of your heat or so is going into that prior layer, where you have about 20% of the heat going into each one of the channels or the ribs. And this part is rotated on a turntable or a trunnion table about the center axis to deposit subsequent layers on this. And we've demonstrated this down to some very thin walls, as well as some fairly large gaps. You do not have to include any sort of filler material in the channels at all. So again, this is forming the jacket and closing out the channels in place. And let's go to the next slide, which will provide a little bit more details on this. So again, similar picture on the lower left-hand side. You can see the image on the right-hand side of the actual process itself. So again, with LWDC, we're starting in an area of stock, and that is key to making sure that you have the proper material built up there in the steps. Again, the angle of the laser, the angle of the wire feed continuously changes as you traverse up the nozzle, and it's a function of the angle of the wall. One of the challenges that we had to go through with the development, and again, a lot of the details in the patent on this, is ensuring that none of that deposited wire is going to melt into the channels. And I'll show some images later of what those cross sections look like, and you can see that it's clean. You don't want any to drop through in there, because we're looking for constant flow areas on this. Again, we don't need any filler material in these channels. There's no post-processing necessary on this. You close out the jacket, and then it can go on to further steps, such as welding on manifolds on that. We've looked at a few different laser energy sources on this, both continuous and pulse. And it's really dependent on some of the materials that are used, and whether you're using monolithic or bimetallic materials. And we are obtaining a robust bond, robust joint at each one of those ribs on there. And again, we've tested a variety of very thin ribs and some thicker ribs, and also the span of the channels. On the left-hand picture there in the bottom, we're just showing a bimetallic application, which I'll get into a little bit more detail on this. The weld wire that we're using for this is a standard off-the-shelf weld wire. We're typically using a very small diameter, which would be on the order of about 0.30 inches, or about 3/4 of a millimeter on the wire. Next slide, please. So I have a few examples here of both monolithic and bimetallic development on this. So for monolithic alloys, we've demonstrated this on a variety of different nozzles in various alloys, including Inconel 625, stainless steel 347. I mentioned the bimetallic there, but I'll talk that in a little bit more detail. Haynes 230, we've also demonstrated this on. Aluminum based alloys such as 6061. And I guess not included on this particular list, we've also demonstrated it with JBK 75, which is an A286 derivative, and NASA HR1, which is an alloy that we're developing for hydrogen resistant applications. And a few other notes about this too, which I didn't show in the prior images, but want to make sure that we point that out, is you can start and stop the process. We've demonstrated that several times, and also the ability to use real-time inspections on this as well, and tracking of the weld melt pool on this throughout the process. So the row of images there that you see in the middle give an example of the progression through this. So again, you're starting off with that liner that's been fully slotted, and building up an area of stock at the aft end, or the larger diameter of that liner, is one of the keys to this, creating that step. Traversing up the liner, again, angles are continuously changing as you're increasing the height on that. So then we have a fully closed out liner that we can go about with further processing. The example here shows that we've applied the manifold weld preparations and welded the manifolds on. In the bottom left pictures there, you can see examples of the closeout and what this looks like. On some test specimens, you can see we're getting robust joints there. We've gone through a lot of the characterization work on that with a variety of these alloys. So I have a pretty thorough understanding with most of the alloys, what type of properties we're getting at the joints on these. And then the bottom right picture is just an example of some other materials. That was stainless steel 347. Again, we've worked 625, Haynes 230, and a variety of super alloys on this. The images in the middle there, that was actually on the aluminum 6061 nozzle. Next slide. So using the same technique, one of the further developments that we wanted to work on was advancing this for bimetallic. Monolithic nozzles are not always the best design option, just based on heat flux environment. So there's times when we need bimetallic materials, such as a copper liner and a super alloy jacket. And some of the traditional methods can be used to do that, but what I probably failed to mention earlier is plating has been used for a long time on this, but it's a very slow process. You have to fill the channel with the wax, and then plating takes a while. I guess the original additive manufacturing, atom by atom. So it can take a while to complete a plated closeout on that, and then you have to melt all the wax out and clean the wax out. Brazing, has been used for many decades as well, but requires a very tight fit up on the jacket closeout to the liner closeout. So one of the advantages of this technology, again, being able to form the jacket in place and reducing the need for those very tight tolerance fit ups on this. So talking a little bit about the bimetallic configurations using LWDC, we've looked at a few different options on this, and as I'll show you in a little bit, have successfully hot fire tested some of these nozzles. So in this particular case, we were looking at a copper chrome zirconium, or C18150. We're also looking at some development on this using the NASA GR-COP alloys. And we've looked at a couple different configurations, which I would call multi-metallic and bimetallic. The example on the left-hand side would be a multi-metallic where we use the copper liner with all the coolant channels slotted into it. And then we use an intermediate alloy on this, Manel or an Inconel on that. And then, one or the other for the closeout on it. On the right-hand side, we do a direct closeout of this where we're using a C18 150 and then direct to a Manel closeout on that. So sometimes using that intermediate alloy, there's advantages of the bonding, and this gets into one of the patents that we have on this as well. And the approach for that is we would start out with a copper liner without the channels in it. You would clad on an intermediate alloy with a very thin cladded layer. Then you slot your channels in there, and then you can close out with a super alloy such as Inconel or Manel on that, which is a copper nickel based material. The advantage of that is copper, when you're trying to do any sort of welding or deposition on, it's just going to pull all the heat away. But if you do that interim cladding process before you slot the channels in there, then we're able to close that out without any issues. And we've demonstrated that on some of these applications here. Go to the next slide, please. Just to give a general process flow of this, which I think I've discussed a little bit, but again, the LWDC process is highlighted there in this process flow. We start with the liner. There's different heat treating that liner has to go through. There's final machining of IML, OML surfaces on that, and then slotting in the channels. In this case, there's water jet milling of channels, which is another technology we've used for forming channels. And then we do the closeout using this process. So again, you start out with a single piece liner and the jacket is formed in place, which also reduces some of the part count compared to some of the traditional techniques where we have multiple piece parts coming in, then you have to assemble through a brazing process. And then you can continue through the rest of the process, such as depositing on your manifold lands, welding on the manifolds, and then eventually getting to the final inspections and proof testing of that. In a minute here, I'll show some examples of some of these nozzles and the hot fire testing as well. Next slide, please. Just another example of the process flow, just shown pictorially here. So again, we've formed the liner, and we do that through a lot of different additively manufactured processes. And then we form the channels into that liner, and then the bottom right-hand picture shows an interim process step of the LWDC, Laser Wire Direct Closeout, of those channels using the prescribed method that I talked about a little bit ago, and then we end up with the final nozzle on that after we weld the manifolds on. So we've reduced the part count on this one, formed the jacket in place, and again, as you saw some of the examples, able to get consistent cross-sectional area on the closeout of all those channels. Next slide. So talking a little bit about some of the hardware that we fabricated and some of the hot fire testing. This was completed to increase the TRL of the technology, taking it out of the lab and actually putting it in a relevant hot fire environment. So we completed several test campaigns over the last few years on this. All this testing was conducted at NASA Marshall Space Flight Center at our test stand 115. We've tested a series of subscale nozzles up to about 2,500 pounds of thrust on it, and we still have a lot of ongoing testing with this. We've used a variety of propellants on this, mostly LOX hydrogen, but have also done some LOX RP on this as well. And we've run it with water is a coolant on this, but we've also looked at hydrogen cooling and RP cooling as well on this. And one of the objectives, a lot of this testing, was to really push the technology. So we ran fairly high chamber pressures. We ran very high mixture ratios on this to thermally cycle this. We went through a variety of cycle testing where we would hot fire, get up to a steady state, shut down, and then fire again on that, with the objective of really trying to push the technology through the various thermal gradients and the thermal cycles on this. So in the bottom picture there, you can see several of the nozzles we've tested, not all of them, but a variety of them there. Some of the starts that we put on those, and then the time in seconds on that. And when we talk about liquid rocket engines, we talk about seconds on it. It's a very harsh environment. So as we build up time into the hundreds and thousands of seconds on that, it continuously shows the proof of the technology in that relevant environment. On some of the bimetallic applications, we've cycled some of those nozzles to fairly high starts. You can see the 18150 Monel nozzle. We've cycled up to about 60 times on that, and we could continue to keep testing that, but we had good performance on that. Next slide. Just here's an example of the setup here, because we're going to show you a video in a minute, and just wanted to show what the setup looks like on this. So we have the LWDC nozzle with all the technology we've described so far, and that we use an additively manufactured combustion chamber on this, which is GR COP, and then we use an additively manufactured injector on this. And this specific example here is LOX hydrogen that we have, and running chamber pressures up to about 1200 PSIG on that. So let's go to the next slide, which I believe is our video.
Yes, Paul, I'm going to pull it up shortly. Just give me 1 second.
And as Jordan's pulling that up, I'm not going to talk through the video. We can talk questions on that, but I think it's better if there's sound with it, if we can get the sound to work on the video. The other thing that I probably should have pointed out with LOX hydrogen, not as exciting of hot fire testing, just because your plume is more or less clear on that. But again, those were all steady state hot fire testing that was conducted. Jordan, if we can go back to the slides. So I guess as the slides are loading on that, we've completed a lot of the testing at subscale. We have a lot of ongoing hardware development at larger scale. We're currently finishing up fabrication of a series of nozzles that are about 35,000 pounds of thrust. So these are a couple feet in diameter. We've also started some of the technology development on larger scale nozzles that would be pushing about 4 feet in diameter and 4 to 5 feet tall on it. So we have our slides back up here. Just some images from the hot fire testing that you just saw the video for. The upper two pictures are on the monolithic applications. This particular one is the stainless steel 347 nozzle. And we've put some data out there on these that one of the objectives of this testing, again, was to really push some of the wall temperatures and the thermal cycling of these. So it's beyond where we'd actually run some of the wall temperatures in the application. But that's the objective of the test itself, is to push it beyond the limits. And then the lower pictures there, you can see some of the testing from the bimetallic application. Again, these are all actively cooled using hydrogen. Next slide, please. So just some of the results, our hot fire testing, really everything performed very well as expected. We've saw the pressure drops as expected on this. The Laser Wire Direct Closeout performed as expected during all the startup and shutdown transients and during all the steady state loads on that, and really met our expectations on this. Beyond some of this hot fire testing, we've done some lab testing as well on bursting some of these, and again met the high burst pressures that we were expecting compared to traditional techniques. So let's go to the last slide here, and we will wrap up and then get into any questions that we have. So just conclusions on this and in general wrap up is we've developed this process. I know this is a very high level overview of what the technology is, and as I mentioned earlier, we have several technical publications out there, including the patents on the technology itself, which is more specific to rocket engines, but certainly can be applied to several different advanced heat exchangers. We've completed that development with both monolithic and bimetallic configurations. We've evaluated a variety of different options for how we do those closeouts, again, using intermediate alloys or using a direct LWDC closeout. We've completed a variety of hot fire testing. We've accumulated over 87 starts, and that number is ongoing, as well as we develop new hardware and almost 5,000 seconds at high chamber pressures on that. And the image on the right hand bottom, you can see that's one of our ongoing developments on a 35,000 pound thrust nozzle. It's a couple of feet in diameter, which use LWDC process. And that particular one there is at Haynes 230, but we've also done this in JBK 75 and NASA HR1. The technology is available, as Jordan mentioned. We've supplied a lot of development data out to vendors and industry partners, some of which are actively working this technology. So it is beyond just the lab at this point, and we've increased the TRL through the hot fire testing and starting to work some of the supply chain side of this as well. So with that, I've concluded the technical portion of this, and I think, Jordan, I'll let you take over for questions, and happy to walk through any of those.
All right, well, thank you. If we did not answer your question, don't worry, we will go ahead and email you a response. And again, I wanted to thank everyone for participating today, and I hope you enjoyed yourself. If you're interested in licensing this technology, you can go ahead and click or type in the link that you can see on your screen right there, and it'll send you to our patent portfolio where you can learn a little bit more or license the technology if you're interested. Thank you again, Paul, and thank you, Sean, for helping me with this presentation. And that's it.